Hi guys, it's your science teacher here, back with another video. This time I'm going to go through the whole of the first unit for physics, which is energy. So without further ado, let's get started with today's video. So the topic of energy is going to start off by looking at the different ways that energy can be stored. And for your GCSEs, you need to know about 8 of the different types of energy stores. And the first one is kinetic, and kinetic energy is energy due to movement. So anything that is moving has kinetic energy. And after kinetic energy, we have gravitational energy, and gravitational energy is the energy gained due to something's position above the ground. So you gain kinetic. The next energy store is gravitational, and gravitational energy can be gained by lifting an object up. So it's basically the height above the ground. The higher you are, the more gravitational energy you will have. Elastic energy is caused by either stretching or compressing something. Just think that if you pull an elastic band, when you let go of that elastic band, that elastic energy is released. The next energy store is chemical, and chemical energy can be found in different fuels, in food, and also in batteries. And chemical energy store is released through chemical reactions. After that, we have an electrostatic energy store, which is the attraction between positive and negative charges. As well as attraction, you can also get repulsion as well. Then we have the magnetic energy store, and this is also attraction and repulsion, but it's not between charges, it's between magnets or magnetic materials. Then we have nuclear energy, and this is energy stored in the nucleus of the atom. And then the final energy store is thermal, which is energy stored due to heating. And what's really important to remember about these energy stores is we can convert between the energies that an object has, but always something remains the same, which is the amount of energy that you have. And this is called the conservation of energy. And basically, it just states that energy cannot be created or destroyed. Now, there are 4 types of ways that energy can be transferred, and the first one is mechanically. And in a mechanical energy transfer, this is when a force is being put on an object. An example of a mechanical energy transfer could be if I was to push a trolley, I'm converting the energy stored in my body, which is chemical energy, into the kinetic energy of the trolley, and this is a mechanical energy transfer. The next one is electrically, and an electrical energy transfer involves if we have an appliance which is being. The next way that energy transfer can happen is electrically, and this is if I have a power source which is connected to a component, then an electrical energy transfer will take place. Just think, for example, if you are using a toaster, that toaster will be plugged in to your mains electricity, and it will be electrically transferring the energy into a thermal store of energy to heat up your bread and make some toast. Then we have heating, which is another way of transferring energy. And there are 3 examples of energy transfers by heating, and we're going to talk about them in a little bit later on in the video. And they are conduction, convection, and radiation. And then finally, we have radiation, which can include light and sound to transfer the energy. If I have a look at this roller coaster and I have a look at some of the energy transfers that are taking place and the energy stores that it has at different points, then if I have a look down at the bottom, what's going to be happening is it's going to go up this hill, the roller coaster, isn't it? So if I just draw a little trolley here, it's going to go up the hill. And as it's going up the hill, it's going to be collecting gravitational potential energy because it's doing work against gravity. And this will be the energy store that it has because it is above the ground. Now, when it falls down this hill, it's going to gain kinetic energy as it falls. And if I have a look at some of the energy transfers that are taking place to go from gravitational energy to kinetic energy, if I think about this roller coaster, it's probably going to involve an electrical energy transfer because it will be a power source giving it this energy. And it's also doing mechanical energy transfer going from gravitational to kinetic energy because there's a force being applied onto this object. The important thing to remember though with these energy transfers is the energy that comes in must come out. So the amount of GPA that it has at the start will be converted to kinetic energy. And assuming that no energy is lost through friction, all of that gravitational energy will be converted to kinetic energy. Of course, with friction, you would lose some of the energy to heat and sound. And almost zero energy transfers are 100% efficient, meaning that we will always lose some energy to heat and sound. If I look at this television and look at the energy transfers that take place inside the television in order to make it work, then I will start off with electrical energy because it will be plugged into the mains electricity supply, and the electrical energy that is coming in will be converted into light and sound so that we can hear what's going on and we can see the pictures on the screen. However, with all electrical appliances, some of this energy is lost, and in a electrical appliance, it usually is in the form of heat. Just think if you leave on your TV for too long and you go to touch the plug, or you even go to touch the TV, it might be quite warm. And this is due to the resistance in the wires inside the electrical appliance, and some of the energy is converted into heat. And we call the energy that we want the appliance to be emitting, we call that useful energy. And we call the energy which is not useful, we call it the wasted energy. Now, it's really important to remember again that what energy comes in must come out of my appliance. So if I put in 200 joules of electrical energy, 200 joules of energy must come out. And for example, if the useful energy is 150 joules come out as light and sound, then I know that 50 joules must have been wasted through heating. Now, what I did here was I looked at what is called a closed system. And the reason why this is called a closed system is because of the fact that energy can be transferred to the surroundings, but matter cannot be. And this is different from an open system where energy and matter can be transferred in and out of the surroundings. I can represent energy transfers using what is called a Sankey diagram. And Sankey diagrams are a great visual representation of what is going on in an energy transfer. So here I have two Sankey diagrams, one for an energy efficient light bulb and one for a old and standard light bulb. Now, the energy that comes into a light bulb will be electrical energy because it will be plugged into the mains supply. So electrical energy is coming into both these light bulbs, and the energy coming out will be the same as well. The useful energy we want to come out of our light bulb is, of course, light. And the wasted energy from a light bulb is heat. Now, as you can see, the old light bulb is giving out much more energy through heat. And you can see this because Sankey diagrams are drawn to scale. This means that the size of the arrow represents how much energy is given out or goes in. So usually with a Sankey diagram, there is a scale, and that scale could be 1 centimeter equals 100 joules. And therefore, in this diagram, if the electrical energy, if this width here is 2 centimeters, that would mean that I have 200 joules of electrical energy being supplied. Now, remember, what goes in must come out. And here, if I've got a width of 1 centimeter, that would mean that 100 joules were being emitted as heat. And this one would also have to be 1 centimeter because remember, what goes in must come out. So this would be emitting 100 joules of light energy as well. Now, in the energy efficient light bulb, this arrow of useful energy is a lot larger. This might be 1.8 centimeters, and down here is heat might only be 0.2 centimeters. So here we have 180 joules being emitted by light, and we have 20 joules being emitted by heat. And from these Sankey diagrams, you can actually calculate the efficiency of these appliances, because to calculate the efficiency of the appliance, what you do is you do the amount of useful energy given out divided by the total input energy. So if I have a look at my energy efficient light bulb, I would be doing 180 joules divided by 200 joules, and that equals 0.9. You can put it in percentage, and that would be 90%. It doesn't matter though, you can leave it as a decimal. Remember, you might also be asked to rearrange the efficiency equation, and if you are, always use the efficiency as a decimal for the rearrangement. We're going to look at 3 calculations to work out the amount of 3 different energy stores. The first one we will look at is gravitational potential energy, which is sometimes given the symbol GPE or sometimes given this symbol E with a little p. That just stands for potential energy. And to get the gravitational potential energy, what you do is you do the mass times by gravity times by height. And all energy is measured in joules. Mass is measured in kilograms, gravity is measured in newtons per kilogram, and height is measured in meters. The reason why I've put it into a triangle like this is because sometimes it makes it easier if you are wanting to work out a different parameter. The way you do this, for example, if I wanted to work out potential energy on top, I would cover up potential energy with my fingers, and the potential energy equals, underneath we have mass times by gravity times by height. But what happens if I don't want to calculate the gravitational potential energy, but this time I would like to instead calculate height? Well, what I would do is I'd cover up height with my finger, and height equals, well, this time potential energy is on top, and that means it's a divide, so it would be potential energy divided by mass times by gravity. Now, there is one way that they sometimes try and trick you in questions working out gravitational potential energy, and that's sometimes using slopes. Now, if this slope is 15 meters long, however, the vertical height is only 10 meters, I would be using 10 meters in my calculation. It's not about the slope's length, it's about the height that it is from ground position. The next one, I'm going to show you how to calculate which energy store is the next energy store we are going to focus on is kinetic energy. And kinetic energy can be worked out using half times by mass times by velocity squared. Now, that's how to get kinetic energy. You just do half mv squared. However, if you wanted to calculate the other parameters, it's a little bit more tricky than last time because you have the squared in the velocity. So let's look at if I wanted to calculate velocity on our own, what I'd have to do. So do the same thing, cover up velocity with your fingers. I'm going to leave the squared just showing so we don't forget about it. So if I was to get velocity squared, I would do the kinetic energy divided by half times by mass. And to get rid of this squared here, you square root both sides. So you'd end up with V equals EK divided by half times mass. And I'm going to put all of this inside a square root. And that's exactly how I would write it into my calculator. Now, there is one way that they sometimes try and trick you with this kinetic energy. Sometimes they will say the words speed and velocity interchangeably. And if you just remember that velocity is the vector of speed, so they will be equal, that is completely fine. Then the last one that we are going to look at, well, the last energy store is elastic potential energy, which is half times by the spring constant times by the extension squared. So the rearrangements are exactly the same for elastic potential energy as with kinetic energy. Now, if I have a look at the units, remember that energy is always measured in joules, so that will be no different. Extension is measured in meters. The spring constant is measured in newtons per meter. Then this is what you would do for units. And finally, the last thing that they could do to trick you with an elastic potential energy equation is they might not give you the extension explicitly. What they might do is they might have a spring here, and what they do is they give you the length that it has originally, and then what it might do is give you the new length, and what you do to get the extension is you'd have to minus the original minus the new length minus the original length. Just before I go on, I do want to focus on the units for kinetic energy as well, because I know that I did miss them out. And that's because I just want to stress for a couple of seconds that they might sometimes use different units, and you have to put them into the units that are needed for the equation. So if I have a look at the kinetic energy, this is obviously measured in joules. It hasn't changed. Energy is always measured in joules, and this one here, if I look at mass in the kinetic energy equation is kilograms, And what they sometimes do to try and trick you is they'll put the mass in grams, and what you need to do is divide it by 1,000 to put it into kilograms, and then velocity is measured in meters per second. Here I have two example questions which I'm going to do. These would be quite high mark questions. That's why I'm going to go through them with you guys. And it says calculate the maximum speed a roller coaster can travel if the height of the drop is 50 meters and the roller coaster train has a mass of 800 kilograms. Assume gravity is equal to 9.8 and mention any assumptions that you have made. So if I just quickly draw out a little diagram, I know my diagrams aren't always the best of what's actually going on. So we have a roller coaster train and it's going down a drop, and gravitational energy is going to be converted into kinetic energy. So the first thing to do is calculate the amount of gravitational potential energy that we've got. And if you remember, gravitational energy is equal to mass times by gravity times by height, and that should give me my gravitational potential energy. So the mass is 800 kilograms, gravity is 9.8 newtons per kilogram, and the height is 50 meters. And gravitational potential energy, or GPE, equals mass times gravity times height, which will be 800 times by 9.8 times by 50. And that gives me an answer of 392,000 joules. Now, it says give any assumptions you've made, and what we're going to assume in this question is that no energy is lost to the surroundings by heat and sound. So because of this, all my gravitational energy is going to be converted into kinetic energy. So I can now say that kinetic energy equals 392,000 joules. And therefore I can now calculate its speed or velocity, because I know its mass is still the same. It's 800 kilograms. And velocity equals the square root of the kinetic energy, which is 392,000 joules, divided by a half, times by the mass, which is 800 kilograms. And that gives me an answer of 31.3 meters per second. And what I'm going to do is I'm going to underline my answer and circle my units to show the examiner that this is my final answer of the question. And also it says, and mention any assumptions you made. So we are also going to write down that no energy is lost to heat and sound. So this will mean that all my gravitational energy is converted to kinetic energy. Now, there is a question below. If you'd like to have a go at it before I go through it, then now would be a good time to pause the video, because I'm going to go through it. So this time it's on about a bow and arrow. And if he's shooting it horizontally, then what's going to happen is this elastic energy stored in the bow will be converted to kinetic energy of my arrow. And it actually gives me the assumption this time. It says assume all the energy has been transferred from the elastic store of the bow to the kinetic energy store of the arrow. So first things first, let's calculate the elastic store of energy. This is my question mark. And I need to know the spring constant, which is 450 newtons per meter. And I also need to know the extension, which in this example is 50 centimeters. Now, this has given me in centimeters, and this is something where it will try and confuse you. So what I need to do is I need to put the centimeters into meters, because that is the unit for extension. So 50 centimeters equals 0.5 meters. Just divide by 100. So to get my elastic potential energy, I'm going to do half times by the spring constant, which is 450 newtons per meter, times by the extension, which is 0.5 meters squared. And this gives me an answer of 56.25 joules. Now, just like the last example, we know that this is going to be converted into the kinetic energy. So I've got 56.25. The mass, there is also a little trick in this one. It's 300 grams. Remember on the last slide when I was talking about sometimes this is how they try and trick you. The 300 grams is equal to 0.3 kilograms. Remember, that's the unit of mass. So just like the above example, V equals the square root of the kinetic energy divided by half times mass. So it's going to be 56.25 on top and a half times by 0.3 kilograms. And let's see what our answer is. And I got it to be 19.4 meters per second. I actually got on the calculator 19.364, and I rounded it up to make it 3 significant figures. We're now going to have a look at 2 other definitions from this topic of energy, and they are work and power. And the work done is the amount of energy transferred. And we can actually calculate the amount of work done by using the equation work equals force times by distance, where work is exactly the same as energy transferred, so it's measured in joules, and force is measured in newtons, distance measured in meters, and the power is the rate of energy transfer, the amount of energy transferred per second. So the way to calculate power is by doing power equals energy divided by time. Now, sometimes we use energy and work exactly interchangeably. So sometimes you might see the equation written down as power equals work over time. They mean exactly the same things. Where energy is, of course, measured in joules, we know that by now. Power is measured in watts, and time is measured in seconds. So now let's have a look at an example experiment that combines both of these 2 terms. Here I have 2 pulleys working with a motor to pull up a weight a certain distance. Now, if I have a look at the one on the right is pulling the weight up faster. And the way I could make it pull up this weight faster is maybe by just increasing the voltage or the current, and this would make it pull up the weight faster. Now, both of these pulleys are doing exactly the same amount of work, because remember, work is equal to force times by distance. And here you can see that both of them have 3 newtons of weight attached to them, and if the distance was 50 centimeters, then the distance would be 0.5 meters, and they're both doing 1.5 joules worth of work. But the one on the left takes 4 seconds in order to pull up that 3 newtons, whereas the one on the right only takes 2 seconds. So in order to calculate the power, what I would do is I would do 1.5 joules divided by 4 seconds for my first pulley, and 1.5 divided by 4 is 0.375 watts. And to get the power of the second pulley, I would do 1.5 joules divided by 2 seconds, which is this time 0.75 watts. So what you can see here is if I have this pulley and it's working faster, then it is more powerful. We're now going to focus on energy transfers that involve heating. And we're going to look at a property of different materials called specific heat capacity. And I think it's best to explain specific heat capacity by looking at some different materials. So down here I have copper, which has a specific heat capacity of around 370 joules per kilogram degrees C. I have some aluminium, which has a specific heat capacity of 920 joules per kilogram degrees C. And I've got some water here, which has a specific heat capacity of 4,200 joules per kilogram degrees C. And essentially what specific heat capacity is it's how easy it is to heat something up. So if I've got 1 kilogram of each of these materials, then copper, because it has the lowest specific heat capacity, is easier to heat up. And actual definitions for specific heat capacity is how much energy is needed to raise the temperature of 1 kilogram of the material by 1 degree C. It explains why when you go to the beach, you burn your feet on the sand and then you can cool them off in the sea. The sand has a really low specific heat capacity, so it heats up really easily. However, the water that's in the sea, that has a high specific heat capacity, so requires lots of energy to heat up. Things with a high specific heat capacity also take longer to cool down generally. This is why you would use a hot water bottle to take to bed with you, because of the fact once you've heated that water up, it retains the heat for quite a long time and will keep it there. Specific heat capacity can be worked out using an equation, and that equation is that energy transferred equals the mass times the specific heat capacity times by the change in temperature. And of course, energy is measured in joules, mass is measured in kilograms, specific heat capacity is measured in joules per kilogram degrees C, and change in temperature is measured in degrees C. And I can do an experiment to work out the specific heat capacity of any material. And you only need a few simple apparatus. You need a circuit containing an ammeter and a voltmeter, something to measure the mass of whatever you're testing, and a stop clock. So I've drawn a little bit of how I would set up my circuit in order to work out my specific heat capacity. Here I've got my ammeter and my voltmeter. I have a power pack, and I would also have, I'm just going to label it as well, I'd also have a thermometer here to measure the temperature of my material. And let's do a step-by-step of how I could work out the specific heat capacity. And the first thing I'm going to do is I'm just going to rearrange the equation and make specific heat capacity the parameter I want to work out. So specific heat capacity is equal to the energy divided by the mass times by the change in temperature. So what I'm actually going to do in this practical is I'm going to have to use a heater in a circuit to warm up a material and measure its start temperature and see how much the temperature increases, and then I can work out the specific heat capacity. So let's see how I'm going to do this in practical. So my first step I need to do is to measure the mass of the metal using a balance. It doesn't have to be a metal, it could just be any material, so I'll just put material using a balance. It often helps if the material does have a mass of 1 kilogram, so then you can actually take this term out because you're just going to be timesing by 1. Then the second step is I'm going to take an initial temperature reading. So you're going to measure the initial temperature using a thermometer. Next, what you're going to do is you are going to heat up the material using a heater. Now, this experiment is not always the best because of the fact you will lose some of the heat to the surroundings. So this is definitely how we can get random errors in our results. Also, we often calculate a specific heat capacity that is much higher because of the fact we have lost a lot of that heat to the surroundings. So we heat up the materials using a heater. Now I can work out the energy that has been transferred to that appliance by doing E equals the voltage times by the current times by the time that I've heated for. So say, for example, you heat your material for 5 minutes. You can work out the energy transferred by turning the time into seconds and then doing voltage times by current times by that time. Then what you're going to do is measure the new temperature, and what you're going to do now is you can work out the specific heat capacity by doing specific heat capacity equals energy divided by mass times by the change in temperature. Now, some things that they might ask you about this practical, they might ask you about what systematic errors might there be. And an example of a systematic error that could arise in this practical is the ammeters and voltmeters not being set to 0. So when you turn them on, they already have a reading on them, and therefore all of your results will be a little bit too large. If we look at random errors that could occur, that could be the fact that you are losing heat to the surroundings. And if we look about what safety aspects there might be doing a practical like this, well, we are going to be working with heat. So one way we could mitigate this is maybe by wearing heat-proof gloves. And because of the electrical equipment, making sure there is no water near any of the electrical equipment. Sticking on the theme of energy transfers by heating, we're going to talk about them 3 modes of energy transfers by heating that was mentioned earlier in the video, and they are conduction, convection, and also radiation. So that first one of conduction, what is it and how does it happen? Conduction is how heat is transferred by collisions from neighboring atoms. So it mainly happens in solids, because in solids, basically the atoms are very close together. So this means that they can collide with one another. Some materials are better at conducting than other materials. Just think about in metals. Metals have incredibly tightly packed structures. If you think about all them positive ions next to each other in lovely, neat rows and columns, well, if we heat up them, they will vibrate next to one another, and that heat will be transferred along the material. Just think what happens if you put a spoon in a cup of tea and you hold on to that spoon. If you hold on for it for too long, that spoon is going to get hot, even though the top of the spoon which you're holding is not actually in the water, but the bottom is, and that heat is being transferred through the solid. Next, we have convection, which is how energy is transferred in fluids. Basically, what happens in a fluid is that when we heat it up, it becomes less dense. So it rises as it becomes less dense, and when it cools down, it becomes more dense and it will sink again. And this is what's called a convection current, and this transfers heat energy. And it can only happen in liquids and gases because of the fact that the particles in a solid do not flow and they cannot move around past each other like they can in liquids and gases. And then finally, we have radiation, and radiation is EM radiation. So for heat, it is IR waves, isn't it? That get emitted, and because of this, it can travel through space. Radiation is the heat transfer that you would feel if you were standing close to a fire. You could feel the heat of that fire coming towards you, even if you're not touching the fire, because of the fact it can travel through the air. When we are designing houses, we want to limit the amount of energy transferred through heating so that our house stay warm for longer. So what we do is we have some clever designs that can help us keep our homes warm. One of them clever designs is double glazing, and the key thing to double glazing is the fact that it has an air gap between the two sheets of glass. And basically, this is so important because air is such a poor conductor of heat. And this means that we can keep our homes warmer because that heat's not going to travel outside of the house. As well as double glazing windows, we also have what is called cavity wall insulation. And basically what cavity wall insulation does is it stops convection currents from building between the walls and transferring heat to the outside. As well as this, it's quite a spongy material, like you can see from the image, and this means that it does have air in between, and remember, air is a poor conductor of heat and therefore will also reduce energy transferred. We do also have loft insulation, and loft insulation works very similarly to the double glazing and the cavity wall insulation. But the key thing to be remembering in here is that all we're trying to do is reduce the amount of energy being transferred to the surroundings and keep all of that heat energy in our houses. Especially in the UK in winter, you know how cold it can get here. I can do an experiment to see which material is the best insulator by doing just a really simple practical. Here I've got some water in a beaker that I've heated up. It could be 100 milliliters, but I just need to make sure it's the same amount of water each time. And here I've got a thermometer sticking out the top to measure the temperature of my water. And I've got some insulation wrapped around the outside, and I have a lid on top to make sure that I'm not getting too much heat transferred to the surroundings. So what I'd need to do first is I'd need to measure the initial temperature of my water. I'd probably heat it up with a kettle first, so it would be around 100 degrees C, but you never know, so that's why I would use my thermometer to measure the initial temperature of the water. Then what I'd do is wrap my insulator around it. Now the key thing with this is I would have to make sure I use the same amount of insulator each time. So for example, I might use 50 grams of the insulator that I use, and I'd wrap it tightly around the beaker. And then after, what I would do is I would leave the water for 5 minutes and then measure its new temperature. Now, what we should see is the temperature should go down over time. And the best insulators, it will have stayed quite a high temperature, and the worst insulators, it will have gone down a lot. So what I need to do after doing it for one material is change the material and repeat the steps, because that is my independent variable. I'm seeing how different insulators are are better or worse conductors or insulators. Now, just looking at this practical setup, I purposely didn't make it perfect to make sure there was a couple of things that I could say about it at the end of how I might go about improving a practical like this. Now, the first thing I would do to improve it is, instead of using a normal thermometer, I could use a digital thermometer. This would make my readings a lot more accurate. In addition to this, I have just got a beaker made out of glass here, and if I was doing it more accurately, then I could use a polystyrene beaker, so I wasn't losing as much heat to the outside. Now we've looked at energy transfers by heating, we are on to the final kind of bit of this unit, which is looking at energy resources and energy demand. Due to populations globally rising so much, we are now almost in a bit of an energy crisis where we are needing to create more and more energy. And the main way that we create a lot of our energy is by using finite resources that are non-renewable. And what this means, this word finite means, is that it will eventually run out. And the finite resources that we mainly use are called fossil fuels. And these include coal, oil, and gas. And the reason why they're called non-renewables is the fact that they take millions and millions of years to form. So you might be thinking, why do we use these? Well, they do have their advantages. They are incredibly reliable. We have been using this technology for a long time. We know how it works, and it doesn't really give up on us. If we want to create more electricity, all we do is we burn more of them. Because of this, we can use it as what's called a base load. This is something that you can rely on to create the bulk of the energy. As well as being reliable and a base load as well, they have been considered to be one of the cheapest resources to run. Now, this might not always be the case, but the reason why we built them in the first place is the fact it was the cheapest option at the time. But using these fossil fuels does have its disadvantages, as you probably know. One of the main disadvantages is the fact that they are finite, so they will run out. As well as this, burning them produces atmospheric pollutants, and we'll go on to a couple of them atmospheric pollutants, and specifically carbon dioxide. They're also not the most aesthetically pleasing things to look at. So you could say that they create an eyesore as well to the environment. They don't look very natural. They don't fit in with the environment. So while we've been using fossil fuels for years and years, we are now having to look at alternatives for a lot of different reasons. Because of the fact they are running out. For example, coal is expected to run out within the next 50 or 60 years. And as well as the fact that we're looking at the atmospheric pollutants and the problems that they are giving us on the environment. So we're going to focus on now the problems of producing the atmospheric pollutant carbon dioxide. And carbon dioxide is attributed to increasing global warming. The reason why carbon dioxide causes global warming is because of the fact it's a greenhouse gas, meaning it contributes to the greenhouse effect. And basically what that means is it forms a blanket around the earth, and it's an incredibly good absorber and re-emitter of heat. So when heat enters our atmosphere, it warms up the planet, and the planet tries to release some of this heat back into space, but carbon dioxide traps this heat in and re-emits it back down. And it's such a good greenhouse gas that even small percentages of increase can have dramatic impacts on the warming of the planet. And because of this warming of the planet, there is going to be some disastrous consequences. We're going to get a much more unpredictable climate. Basically, what I mean by this is that there's going to be more increased droughts. There's going to be more increased precipitation in some areas, which could cause flooding. And we could even get lots of fires. And we've been seeing this pattern happening around globally already in places like Australia and California. You might have seen on the news, they've had tremendous disruptive fires sweep through parts of the country. As well as this, we're also going to get coastal flooding, and this is because of the fact that the polar ice caps are melting. And as well as the polar ice caps melting, this is destroying the habitat of thousands of different species that live in either of the poles. If you've watched David Attenborough's new series about the frozen planet, you'll have seen all of the disastrous consequences to the different species of wildlife, like the polar bears, from the polar ice caps melting. In addition to this, disease will spread more quickly as well, because of the fact things like the parasite that causes malaria that can travel further. Malaria likes to live in warmer climates. The parasite does that. It's in mosquitoes. Well, then mosquitoes can travel further if the climate warms up elsewhere, and they can carry that parasite with them. I did say the destroying the habitats. Well, it's not just the polar region that will be affected. It will also be different habitats as well. Just think about coral reefs, for example. Because of the fact they are warming, they are bleaching. The coral polyps inside them actually die when the ocean warms up. And that is one of the ecosystems that's being severely affected by this warming of the planet. But it is not all doom and gloom. We can do something about it. There is alternatives out there in which we can get our power supply from, and we are going to look at quite a few of them just shortly. But first, I'm just going to show you the generics of how power stations actually work that burn coal, oil, or gas. And the basic principle is that we heat up that coal, oil, or gas. That produces steam, which turns a turbine, and that turbine works a generator. And this generator basically spins a coil of wire in a magnetic field, and this creates a current, and this is what the electricity actually is. And then we use a step-up transformer to increase the potential difference, and then we send it across in pylons all over the country to where the electricity needs to go to. You might say, well, where does the steam go? And you might have seen them huge cooling towers by power stations. In fact, most of the infrastructure in a power station is them cooling towers, and most of them are emitting steam. It's usually the really thin tower that emits all the carbon dioxide and sulfur dioxide and other atmospheric pollutants into our environment. So we're now going to focus on some resources which are renewable, and these are also sustainable ways of generating electricity. Renewable means they are not going to run out, and sustainable means that they will meet the needs of today without hindering future generations. So let's focus on these two methods that we have in front of us. And the first one is solar power. And solar power works by using the sun's light. It contains what's called photovoltaic cells. And these photovoltaic cells turn the light into electricity. And then over here on the right, we have wind power. And wind power works by turning kinetic energy of the wind into electricity. Now, both these techniques are great for the same reasons and also have very similar disadvantages, and that's why I kind of paired them together. Now, their advantages is the fact that they are renewable. This means that they are not going to run out anytime soon. But they do also have these disadvantages, and we are going to talk about them as well. So, the first advantage was that they were renewable. As well as being renewable, they also do not emit any harmful pollutants into our atmosphere. But they do have the disadvantages, and this is why we don't see our fields full of solar panels and wind farms. We do use them, but they are not used as our baseload because of the fact they are not as reliable. Sometimes they do not produce as much electricity as we need. For example, just think if it's not a windy day, then we're not going to be producing enough electricity. And for example, solar, if we have a sustained period where there's not as much light, maybe because it's quite cloudy and therefore there's less light reaching the solar panels, then they will not be producing as much electricity. They also produce less electricity in the winter because there's less sunlight during the day. So as well as being unreliable, they also require large amounts of land. This land could be used for farming, it could be used for building houses, so you've got to take this into consideration when producing these sustainable resources. As well as needing large amounts of land, they can be quite expensive if you want to use them to produce lots and lots of electricity. But what you have to remember when building a wind farm or a solar farm is once you've built it, then you aren't going to have that many running fees. You're just going to basically not need to pay for any fuel whilst it's there. I suppose I could add that to an advantage is the fact that you don't need any fuel. The next two techniques we're going to have a look at involve the sea, and these are tidal electricity plants and also wave. And these both work on using the water's kinetic energy in order to turn a turbine and create electricity. But the problem with both of these techniques is the fact that there's not very many suitable locations in order to make much electricity from this. For example, you need the coast to be a specific shape in order for this to work, and you need to make sure you've got somewhere with where the tide goes in and out very well. So it's really hard to pick a desirable location to build these. But the main advantage of tidal is that tides are very predictable and we can generate loads of electricity using this. And in the locations where they are suitable for tidal, then we do use this quite a lot to produce a lot of the electricity. Wave, however, is a lot more unpredictable. You don't know whether the swell will be good that day or whether you are not going to get big waves. So it's a lot more unpredictable. Just like wind and solar, it's potluck on how much electricity you will be producing. We're now going to have a look at two renewable resources that have been used in different countries as baseload producers. And these are hydroelectricity, which is over here, and also geothermal, which is over here. Now, the reason why we can use these as base loads is I can vary the amount of electricity I'm producing, and they are incredibly reliable. So if I have a look at hydroelectricity over here, how does it actually work? Well, what I do is I let water down in intervals to turn turbines, and this is how I create my electricity. So as you can imagine, it's great and it has very similar advantages and disadvantages for geothermal. So we will do them in a second. But like I said, for both of these, I can use these as base load renewables. This basically means I can depend on these resources to make my electricity needs for a whole region or country. And geothermal works by using the Earth's heat. And what we do with the Earth's heat is we heat up water, which creates steam, turns a turbine, which goes into a generator, and voila, we have electricity. So just like last time, we will create some advantages and disadvantages for these. Well, the main thing for their advantages is just like with solar and with wind, we are going to get no harmful atmospheric pollutants. Also, it's entirely renewable. I'm not going to run out of it. And also, there's going to be no fuel costs again. So you might be thinking, well, these two sound great. These can be my base loads, so we should just use these. But unfortunately, they do have their disadvantages as well. The main one being the fact they can be incredibly expensive to produce. Hydroelectric power stations are quite pricey. Same with geothermals. And with geothermals, they can only be used in certain locations. So for geothermals, they need to be created where the Earth's crust is incredibly thin so I can get to that heat. The same thing can also be said about hydroelectricity. Because you're going to be flooding lots of land, you can't just create a hydroelectric plant wherever you want to. For example, if there is infrastructure already in place, like people's houses, people's factories, you can't plop a hydroelectric power station there because it would flood large areas of land. Also, geothermal and hydroelectricity can have some negative effects on the environment as well. For example, geothermal, when you dig into the ground, you can get some harmful atmospheric gases. With hydroelectricity, you might be flooding animals' habitats and therefore ruining the ecosystems that are already in place there. We are going to look at another renewable technique now, which is often used in transport because we need energy not just for our power stations, but also for how we move around. And this is, of course, biogas. And we create biogas by burning crops and other organic matter in order to generate electricity or in order to power a car or even an aeroplane. Now, this technique is what we call carbon neutral. And it's carbon neutral because of the fact we are burning material, so we are going to be putting carbon dioxide into the atmosphere. However, when these crops are growing, they are going to take carbon dioxide out of the atmosphere. So we describe this as being carbon neutral. But as you can imagine, if we were to power all our transport from this, we would need an incredibly large amount of land in order for this to be possible to power all of our vehicles. And even if you wanted to use it for electricity, you would need such a vast amount of land in order to use this. In addition, not everything In addition, nothing can be totally carbon neutral because just think about it, you're going to be transporting this around places and therefore it might not be 100% carbon neutral. So here is another technique with pros and cons. And as you've seen with all of these, they all do have their pros, they all do have their cons. And that brings me on to the last energy resource that I'm going to talk about with you, which is nuclear energy. And this is perhaps the most controversial out of all of the energy discussions that I have, especially with my classes. I think there's always about 50% who love nuclear and 50% who don't agree that we should use nuclear. Now, nuclear is a finite resource, meaning eventually it will run out. However, we do have incredibly large reserves of this finite resource at the moment. And the reason why we have large reserves and it not being a massive issue is because of the fact nuclear is an incredibly efficient way of generating electricity. I think it's 1,000 kilograms of coal produce the same amount of electricity as 1 kilogram of uranium. As well as being efficient, this could be used as a base load as it's incredibly reliable. This basically means that if I want to make more electricity, all I do is I turn up my reactor and I have more fission taking place. And doing these reactors and carrying out this nuclear fission, I'm not putting many atmospheric pollutants into the atmosphere. So what I'll do is I'll put a smiley face next to all of the ones that so far have been really good for nuclear and a ticks in the boxes, but unfortunately it's not all smooth sailing. Carrying out nuclear reactions can be a little bit dangerous. And this was seen in Chernobyl when the nuclear power station exploded. They were carrying out some tests on the reactor, seeing how much electricity they could produce, and the power station exploded. And when you're working with radioactive material, you produce what is called radioactive waste. And this radioactive waste can stay active for thousands of years. So finding safe ways to dispose of this can be incredibly tricky. And because of these dangers and radioactive wastes, you need to really find a suitable place to put these reactors. So, for example, building these where you have a fault line where earthquakes are going to happen or volcanic activity happens is pretty much a no-no because you don't want any nuclear waste to escape. So you're going to have to think about the location where you build a nuclear reactor. Okay, so that brings me to the end of this video. I know it's a long one. Energy is quite a long topic, but thanks for sticking all the way to the end. Remember, if you did find this useful and you liked it, drop it a like and subscribe to the channel.